As we all know, climate change is a constant battle between achieving environmental sustainability and an economy that relies on consumerism. Protest after protest or post on Instagram, we hear that the real solution is banning single-use plastics, stopping oil production, awareness, or simply looking for a solution. Anyone else tired of this? Me, because clearly these solutions aren't significant or efficient enough. How we actually tackle this problem is through technological advancements and making clean energy our top priority. How can we do this? By building a solar farm in space. Okay, hear me out. In our status quo, the policies and organizations set in place are rooted too deep. Government officials have a conflict of interest. Sorry, wait, what? There's a clear conflict of interest. If we were to put financial restrictions on the growth of oil companies, that would create an economic recession. Because we see that too big to fail companies like Shell, an oil company, are crucial to the sustainability of our economy. While at the same time, they are a stub to environmental growth and a significant polluter. Every year, the 5 largest oil and gas companies spend approximately $200 million on lobbying designed to control, delay, or block binding climate-motivated policies. Let's stop pointing fingers and switch gears. We can continuously grow our economy while still consume at our current rates. To understand this, it's crucial to note that climate change is not a problem. It's a result of multiple problems accumulating to that result. One of those problems is the energy sector. Humans have changed the natural greenhouse gas balance through burning fossil fuels and oils. Let's focus on that. Why do people choose oil over renewable energy? Because it's cheap. End of story, period. There's no big explanation as to why. If you were to personally choose solar energy over oil, obvious sacrifices must be made. Solar tech just isn't good enough. Solar energy isn't as efficient as oil, so it jacks up the price. The average solar panel is in the efficiency range of 15% to 22%, whereas oil's efficiency rate is 85% and only 15% is lost in conversion. If we made solar energy even more efficient than oil, solar energy wouldn't be considered a second choice or a sacrifice. So less propaganda or persuasion will be needed. If sustainable alternatives were the first choice economically, then people will naturally want to make eco-friendly choices. If being a good person meant that you were richer, then everyone would want to be Gandhi. Frankly, solar energy just isn't efficient or reliable enough. How can we solve this? Launching solar panels into space. The sun's energy is infinite, constant, and abundant. The sun's total power that hits Earth in a single hour can power what the entire world consumes in a year. That's wild. We just need to get better at harnessing that power. A lot of the sun's energy is reflected back into space by clouds, atmospheric particles, and bright surfaces on the ground. And further, more is absorbed in the ozone and atmosphere. Solar rays are filtered through the atmosphere, and a lot doesn't even hit Earth. There's so much more energy that we can harness if we put panels in front of the filter. Obviously, solar panels only work for half of the day, and solar energy isn't affected by nighttime. So the energy you get is constant in orbit. So regarding the efficiency problem, we already get twice as much energy from the sun when we put panels in orbit. However, a significant amount of energy is lost during conversions. Solar panels transfer electricity through wireless power transmissions. There's a lot of technicalities involved in increasing the efficiency of wireless power transmissions, let alone the efficiency per solar cell. Let's look at wireless power transmissions. To understand this, we got to understand that solar space panels consist of 2 main components. First, the satellite in orbit. Second, the receiver station on Earth. Solar power satellites are launched into orbit. They would receive sunlight and transmit wireless energy back onto a receiver station on Earth. The photons, sun's rays, that hit the solar PV panels have to be converted into electricity by the cells, which converts into microwaves. Microwaves get beamed down through the Earth's atmosphere to hit the receiver stations on Earth. The receivers would have to transfer microwaves back into electricity. There's a lot of conversions that have to be made. As you can imagine, lots is lost just with transportation. Shockingly and perhaps embarrassingly, only 9% of the energy received in space will reach consumers on Earth. If more energy is received originally in space than it would on Earth, the energy we are able to receive isn't that insignificant. Let's look at this theoretically. A solar panel in space receives, let's say, 100 joules in a day. However, it can only really use 9% of it. In the end, you get 9 joules. A solar panel on Earth only receives 50 joules in a day if we account for nighttime. So 22% of 50 is 11. You get 11 joules. Although solar panels on Earth are more efficient, it is dependent on atmospheric weather, nighttime, and seasons, adding to that unreliability. So you might not always get 11. Whereas space solar panels eliminate those factors and purely focus on optimizing the efficiency of a solar cell. Although lots of energy is lost in conversion, there's much more potential to innovate better technology to harness that energy better. We can do this by optimizing and being selective about what parts of the system and satellite models to use. For example, SPS-1, a model of solar space satellite, uses lasers instead of microwaves. Lasers work faster and concisely in space. To optimize efficiency, we can use a combination of both lasers and microwaves, where each form is used when it's in an environment where it works most efficient in. The SPS-3 model requires less complex power management and distribution of arrangement. The process is moved by direction than light, rather than physical electrical infrastructure. The model is a reflective system where it uses mirrors. Unlike SPS-1 and SPS-2, it doesn't require photovoltaic panels, but uses mirrors. It collects lights with mirrors to bounce them down to smaller PV panels that will convert that energy into microwaves, beamed down to Earth. JAXA and NASA are working on projects specifically using the SPS-3 model. JAXA is planning to launch its solar panel in orbit by 2030. They designed a model that uses 2 large solar reflectors, and the reflectors would focus that light received from the sun on a collector. The collector converts energy into microwaves that will beam down to the surface of Earth. NASA is working on an SPS alpha model. It's in the shape of a giant bell, and the bell will capture the energy and funnel it into a PV collector before it gets beamed down. Beyond optimizing efficiency per cell and conversions, there's a lot more to figure out. Solar panels on Earth last for about 30 years. How do we create robust structures to avoid the disturbance of asteroids? How do we dispose of that waste? Currently, there's a huge problem with space junk. Do we just follow an escapist mindset where space is a new trash can? Absolutely not. We gotta figure that out. Perhaps we could reuse solar panels, following precedent as what SpaceX is doing with rockets. To make the launch easier, we can also add elements of self-assembly, such as using origami. For the time being, we have to think bigger, to think beyond what government policies can do. Remember, if clean energy became more efficient, it lowers the price, eventually to an ideal point where solar energy becomes cheaper than oil. Where we live in a world where non-negotiably being green is the first choice. Solar energy faces problems such as efficiency and reliability. Solar space farms are a definitive answer to improving technology and moving us into the right direction of prioritizing green energy.